Hello everyone, welcome to 360DigiTMG. In our today's session, we are going to discuss about fundamentals of deep learning, their concepts, layers, and activation functions. I am Dhanashree Meshram and I will be your speaker for this session. In this webinar, we will walk through a complete life cycle of how to build a deep learning model. Start from data ingestion till all the way to deployment. We will discuss how data flows through neural networks, what each layer does, and how activation functions bring these models to life. We will also explore optimization, evaluations, and regularization techniques that makes our model efficient and accurate. So let's start our session. Here, in our first pipeline, we'll have our data ingestion and pre-processing. So here, this is a deep learning, which will act like a fuel in our Power AI. A data ingestion is a process of collecting and importing data from various sources, from various databases, like from web APIs, from sensors, from particular databases. Okay, we'll collect the data from there, and once this injected pre-processing prepares, and it will take there are multiple pre-processing steps involved. Like we will have typecasting. Typecasting ensures that each column will have a correct data type, like integer, float, categories, likewise. Then there is outliers analysis. It will identify and handling the extreme values. What are the extreme values within our data set? If there are certain extreme values within our data set or not. If there are extreme value, what we can do for that? Okay. So different other techniques for doing outlier removals. Okay. Then there is imputation. Imputation we do for filling the missing data. If there is missing data, how we can, if there is missing data within our data set, okay. If there is, then what steps we should take to remove that missing data or to replace that missing data. Then there is discretization, which will convert a continuous data into some bins. Okay. Then there comes dummy variables, which will make the encoding, which will make them a encoding categorical features. Then we will have a feature transformations or feature scaling, we can say. Okay, so feature scaling will be normalizing or standardized to bring a features to a same scale. All features, there are different columns will be available in our data set. So we want all the columns should be aligned, or it should all be in one scale. Okay, for that we will do feature scaling. Then there is transformation and selection, wherein we will create or choose the best features from them. Okay. After pre-processing, we will ensure our model learn from clean, consistent, and a meaningful data from here. Okay. So there are other auto pre-processing libraries or auto EDA libraries also available. Like we all know, Detail is there, SweetWiz is there, and so on and so forth. After we'll get some insights from the data, we will move forward and build a model. Okay. So model building is where we construct our neural network. It involves selecting the right architecture, layers, and as well as hyperparameter tuning is required. Now, hyperparameters are values which are nothing, but it learns by the model itself. Like there are learning rate, batch size, numbers of layers. These are all tuned using different techniques called as hyperparameter tunings, just as Greed Search CV, which tries what Greed Search CV do. So it will tries every combination of the parameters. Okay. Then Random Search CV, which will randomly select combination. And Bayesian search CV, which will learn from the previous styles to improve the search. Okay. Then there is hyperopt. Hyperopt is generally useful for deep learning. Where there is a smart, scalable methods, it is generally useful for deep learning models. Okay. Then after that, we will create a model architecture. So within a model architecture, we will have input layers, we will have hidden layers, and we will have some output layers. Okay. So this is our input layers. Okay. Our clean processed data, then we'll input this into the input layers. Okay. The input layer accepts the raw features. Okay. All the features which are present, like all the columns from there. And then we will feed them into the hidden layers. Now, hidden layers will do what? Hidden layers will perform computations. Okay. So in the hidden layers, we will have all the calculations within the hidden layers, all the computations and forming the patterns, recognizing what is present within the uh, uh, input features, what need to be predicted. Likewise, all the features will be extracted within the hidden layers. And at the end, in the final layers, what will happen in the output layers? It will produce the final result. Okay, based upon the input features and whatever it has been trained within the hidden layers, it will then, from these patterns or whatever it has learned from this, it will give us the output. Okay, so this learning process involves a forward pass. Okay, that it involves a forward pass. Like input will flows through the layers and it will form some output. Okay, it will form some output from this. Now what will happen? We'll check with the actual prediction. Okay, there will be one loss function there. Okay, whatever has been predicted. Okay, predicted with the actual prediction, which is the actual value minus predicted value, will give us the losses. Now, for all the inputs, we will have a collection of all the losses, which is also called as a cost function. And then, after measuring this loss function, or what we can say a cost function or summation of all the loss functions, it is a cost function. So, all the values, now what we want to reduce this loss. We want to reduce this loss. So, what we can do? We can back propagate this. We will adjust the weights. We will adjust the weights within this hidden layers. And we'll try to again minimize this losses. Okay. So, this cycle will repeats across multiple iterations or epochs during the training itself. Okay, forward pass and then going backward. Then again updating the weights, again updating the weights here, again updating the weights here, again updating the weights within the hidden layers, and then again giving the output. Again, we will find out the loss function with the actual value minus the predicted outcome, and we will get the loss value. The collection of all the loss value, which is called as a cost function, it will then again, we want to reduce this loss. We want to minimize this loss. For that reason, we are again back propagating it. Again, we will adjust this weight, and again this process will continuously follows. Okay, so there will be multiple iterations and epochs during training of the models. Okay, and here comes one term which is called as activation maps or activation functions. Okay, so let's discuss on what is activation functions. Okay, so activation functions, there are different or multiple activation functions are there. Like activation functions are what? First we will discuss about that. So activation function brings non-linearity into the neural networks. Okay, so it helps them learn from a complex relationship within a data. What is the data? Within that data, what is the relationship? What outcome is related to what? Okay, what feature is related to what? Likewise. So let's look at common activation functions. Okay, so there are sigmoid activation functions. Okay, this is the formula for a sigmoid activation function. Then there is a tanh activation function. The sigmoid activation functions are generally used for binary output. Okay, so what is the use for the sigmoid activation function? It is smooth and interpretable. Likewise, what are the drawbacks of this? So the vanishing gradient appears. Still, the vanishing gradient issue will be appearing. What is vanishing gradient descent is? Once this all the losses, okay, once all this training, the loss are not changing even after applying multiple times, all like we are back propagating every time and we are adjusting the weights. Still, what is happening? Still, the loss is not changing. The loss function is not changing. At that time, we will understand that there is an issue called as vanishing gradient descent. Okay, so there are different activation functions from which we can overcome this. Okay, so these are the sigmoid activation function. Then there is a tanh activation functions. Okay, so tanh activation functions, their value ranges from -1 to 1 plus 1. Okay, so the pros of this tanh activation function is it is zero centered. Okay, it is zero centered means the value ranges from -1 till +1. Okay, the linearity will be there. The slight linear it will be. Then there comes a ReLU activation function, rectified linear unit. Okay, so it ranges from 0 till, it comes 0 till infinity. 0 till infinity. Okay, and these are all the families of the ReLU, like leaky ReLU, shifted ReLU, GeLU activation functions. These come all from the ReLU family. Okay, so ReLU is fast and it will have a 9 neurons. Okay, then we'll have leaky ReLU, which is also a family from a ReLU only. Then we will have parametric ReLU. Then we will have GeLU, which is also from the family of ReLU only. Okay, so that is a Gaussian linear unit based on ReLU plus sigmoid. These are computed, which is GeLU activation function. Then there is one last, that is softmax activation function. So softmax activation function is generally useful for multiple classes or multi-class outputs. Okay, just like sigmoid activation function is used for binary classification since the value is 0, 1. Only two values, like either it is 0 or either it is 1. Okay, but in the softmax activation function, we'll also have 0, 1 and summation of all the like values. Okay, then it is generally useful for multi-class outputs. And it is related to what? The pros is that it is related to probabilistic approaches. Softmax activation function is generally useful for like probability. Okay, probability of happening A, probability of happening B, probability of happening C. Likewise. Okay, so the use, what is the use? When to use which? When to use which activation function? So we can use sigmoid activation function when there is a binary classification. When there is softmax, we can use multi-class classification. Likewise, depending upon the requirement, we can use multiple activation functions. Like we can use ReLU or leaky ReLU in hidden layers itself. Like within our neural networks, within a hidden layers, we can use ReLU or leaky ReLU activation functions. And we can also use GeLU activation function or switch activation functions in advanced models like transformers and others. Okay, so choosing the right activation can drastically impact learning. Okay, and convergence also. Okay, so let's get back into our deep learning primer part. Okay, so we have discussed about what are the different activation functions. Now, within a neural network, as we all know about like when to use which activation function now. So there are some, after building our model, and we will check it for model evaluations. Okay, before model evaluation, we will check about like output layers, like when to use which, like if there is a regression problem. For example, if there is a regression problem, which activation functions we can use? We can use linear regressions, or we can use linear activation functions or identity activation functions. Likewise, if there is binary classification, we can use logistic regression also. Okay, so here what we will use, we can use a sigmoid or a tanh activation functions, because sigmoid and tanh activation function values ranges from, sigmoid ranges from 0 or 1 and tanh ranges from -1 till +1. Likewise, depending upon multi-class classification, we can use softmax activation function. Okay, so depending upon our output, or what we can say output variable or a target variable, we will decide what we should take as an activation function. Okay, so after that, after training a model, we will come into a model evaluation. Okay, so within a model evaluation also, we will have if it is a regression problem or if it is a classification problem. If it is a regression problem, we can use mean squared error, mean absolute errors, root mean square errors, or uh, mean absolute percentage error, MEPE. So correlation coefficients, these are all we can use when our output variable is continuous. Okay, when our output variable is numeric. Okay, so likewise, if our output variable is classification problem, if our output variable is like having classes, so for that, what we can use? Confusion matrix we can have accuracy, we can have precision, recall, F1 score, okay, cross entropy loss function. Likewise, we can use, okay, depending upon our model evaluations, like depending upon our, if our output variable is continuous or a categorical. Okay, likewise, we will have some optimization techniques. Okay, so optimization techniques, like why we use optimization techniques? So optimization techniques are used to reduce the losses. Okay, next. Okay, so optimization techniques are generally used to reduce the losses and improve the accuracy. So we use optimization algorithms for this. So here we can use a gradient descent, we can use momentum. Okay, so based upon, there are in gradient descent, we have different types of thing. In momentum, we will have different. In Nestello gradient also we will have Nestello momentum. These are all the optimization techniques. Okay, ADA delta, ADA grades, ADAM. Likewise, there are multiple RMS prompts. Depending upon the optimization techniques we will use. Okay, so these are generally used to reduce the losses and improve the accuracy. Okay, likewise, we will have a regularization techniques as well. Okay, so regularization techniques is generally useful for preventing the overfitting of the model. If our model should be right fit, it should not be overfit or underfit. So for this, we will have a regularization techniques, like we will have early stopping. Okay, we will stop our training when a performance of the model is stopped or it is not that improving. Okay, then there is dropout, drop connect. We will randomly ignore some neurons or weights within our hidden layers. Then there is batch normalizations, which will standardize the layers to speed up the training. Then there is noise injections, which will add the randomness in the data. Okay, then there is a data augmentation techniques. Like if we want to add some data within a model, like we can add rotation, we can apply flipping, we can apply exposure, we can apply, there are multiple ways, shears, and so on and so forth. Okay, like cropping or adding noise within our data. Likewise, these are all the things which all comes under what? Data augmentations. Okay, so then there is weight initializations. Weight initialization. So it is a smart starting point for faster convergence. Okay, when we want a faster convergence, we can use a weight initializations. Okay, so these tricks will help model perform better on a new or an unseen type of data. Okay, so after building our model, after checking our model in our model evaluations, after using all the optimization techniques and regularization techniques, optimization techniques, why we use? We use it to reduce the loss. and improves the accuracy of the model. Likewise, in the regularization techniques, we use regularization techniques to prevent the model to be overfit. It should not be overfitted. It should be right fit. Okay, so after doing all this process and checking our model in a model evaluation, we will deploy our model. We'll deploy our model. So we can deploy our model in like mobile apps. We can deploy in web applications, mobile app in the like on-device inference, in dashboards. Okay, like in web applications. If we want to deploy a model on a web applications, we can form on dashboards or real-time tools we can use. Or we can have an API keys. We will connect a model through other software likewise. Okay. So these are all the things from here. And the summary from here is we have understood about what? We have understood about how to collect the data from different sources. Okay, we'll inject the data. After collecting our data, we will do a data processing. After having a data pre-processing, we will form some insights from there. Okay, by using our auto EDA libraries. After that, we will use our model building. Within our model building, we will use a hyperparameter tuning. We can use our optimization techniques. We can use regularization techniques, and we will train our model. Okay, we'll train our model. This will be our input layers. This will be our hidden layers and output layers. And continuously, we want to reduce the losses. So for that, we will do a back propagation every time. Okay, we will run multiple epochs and iterations for multiple iterations. Okay, so likewise, we have understood about like for different types of, if their output variable is continuous, what are the evaluation metrics? If the output variable is categorical, what are the different evaluation metrics? Likewise. So let's enter into our practical part. So within our practical part, we are using a TensorFlow framework. We are using a TensorFlow as a TF. Okay, we are calling from TensorFlow keras.model. We are importing our sequential. Okay, sequential, we are importing from our keras library. Okay, so likewise, we are importing layers, we are importing optimizers, and from the optimizers, there are multiple optimizers as we have seen right now. So from there, we are importing our Adam optimizer. Likewise, there are multiple others, AdaBoost, RMS prop, likewise. Okay, so from here, we are calling callbacks, we are calling our early stoppings. We are calling from TensorFlow.keras.regularizers. We are importing our L2 regularizer. And these are all the necessary libraries which we are importing, like train, test spread, standard scalars, matplotlib for plot. Okay, so here we are taking our data set. Our data set will have an output variable, which is a classes of 2, which is a binary classification model. Okay, so we are directly taking our data. Okay, so we are importing our data from a sklearn. We are taking our data from a sklearn.data sets. Okay, and we are importing a make any randomly or synthetic data we are creating, and we are making like 2 classifications of this data set. We can see here in a variable explorer also, we are taking one data set and we are making this thing. Then we are splitting our data. This is a synthetic data. We are not taking any pre-trained data set. Okay, so we are splitting our data into training and testing, and then we are initializing our model or standardizing our things. Like we are using our standard scaler. These are all the pre-processing steps which we are doing. Okay, then after that, we are initializing our model by using sequential. Here we are adding our dropout. Okay, here within this, these are all the orders within which our model will have. Our model will run. Okay, within this, you can see within the hidden layers, we are using our activation functions, ReLU activation functions we are using. And at the end, since this is a classification problem, we are using our sigmoid activation function. So after that, we are compiling our model and we are fitting our model. Now we have compiled our model and the matrix, we are taking it as an accuracy. Why we are taking it as an accuracy? Because our problem is, what is our problem? Our problem is output variable is classification. That is why we are taking an accuracy as a matrix, evaluation matrix. Likewise, we are using early stopping, wherein we are using patience of 5. We are using epochs of 50 and the batch size of 32. Okay. So we will run this model and we can see the accuracy of the training model versus validation accuracy. Okay, so you can see here the training accuracy and validation accuracies are in line to each other. That means that shows what? That shows our model is right fit. Okay, so both should be in line to each other. And our losses are also somehow in line to each other. If they are not in line to each other, what we can do? We can have an optimization techniques we can apply. Or if there is overfitting, we can use a regularization techniques like early stopping, dropout, patch normalizations, so on and so forth we can add. Okay, so this is it for today, guys. I hope you understood all the fundamentals of deep learning. We'll meet you in the next lecture with a new topic. Thank you for joining.